Welcome to the next lecture on earthquake resistant design of structures. This is lecture number 10 and this would be included in module 3. In this module, we would be specifically talking about the building configuration, the masonry buildings and their design, and we would also be discussing about certain codal provisions related to the earthquake resistant design of structures. The types of construction that we have are basically two types. One is the framed construction of structures, and the other is the box type construction of these structures. In the framed construction, for which we have studied in module 1 and 2, the earthquake resistant design and analysis and design were both done for the framed construction. While as the box type construction is predominantly the type of construction that involves the load bearing structures, or it could also include the shear wall configuration. Now, there is a difference between these two types of construction. In the framed construction, there are structural elements which are mostly beams, columns, and slabs, besides footings. In the box type construction, the walls, which are either unreinforced or reinforced, they act as the load transferring mechanisms. Now, in relation to the earthquake, when there are lateral forces acting on these structural elements, what we have studied in module 1 and 2 is that in framed construction, the base shear is determined, which is then used to determine the maximum shear forces and the maximum moments in the beams and the columns, for which the ductile mode of design is adopted for designing the structure for earthquake. In the box type construction, the earthquake phenomena is much more complex to be designed because it involves the wall configurations, their reentrant corners, and we have the slab, which is not monolithic with the walls in the box type construction. Besides, the slab is a structure which is made up of concrete, while as the walls are made up of masonry mostly, thereby not being a monolithic structure. The transfer of the loads is much more complex in the box type construction, so the analysis is also not as simple as is in the frame construction for earthquake resistant design. Thereby there are certain guidelines that are given for this type of construction for earthquakes in various codes that we would be studying in the next lectures that we will be covering under this module for this course. There could be another combination, which is the combination of the framed system and the shear walls. Now, this combination is quite effective combination, and the earthquake codes they mostly mention that for lateral loads, such combinations need to be designed such that the frame construction takes around 25% of the lateral loads that are acting on the structure at the particular story level, while as the shear wall takes around 75% of the lateral load. Now, this mechanism is preferred as compared to just shear wall or just frame construction. Now, the combination of framed and shear wall system makes the system much more efficient, and it also helps in uh, um, balancing the mass in the structure. Thereby, the static eccentricity of the system is also well placed and balanced within the structural system. So we when we talk about the structures, we are basically talking now structural systems. We are basically now talking about either the framed or the box type construction, or we are talking about a frame plus shear wall construction for load transfer mechanisms for earthquakes or for lateral loads. What we have studied up till now is that we have studied that how do we analyze the framed system for earthquake resistant for earthquake loads, and the loads that were mostly considered were taken from the response analysis of the earthquakes for the particular frame loading systems. Then we also studied about how the design methodology is done, and the ductile design methodology was adopted along with strength methodology in order to design the structural system consisting of beam column frame systems. Now we up till this point we know that the the amount of reinforcement, the section size, the grade of concrete that is to be used, and the detailing of the reinforcement as such. Now, in IS 1893, what is given in addition to this is the structural features of the system as a whole. Now, that also has something to do with the behavior to the earthquakes of the whole structural system. The first one of these is the torsional irregularity in the structural system. Now, these are all plan irregularities. These are given in IS 1893. Now, what is given is that if there is a vertical component of a seismic resisting system, then if it is located somewhere in the system, that could mean that the mass is distributed on one side of the system. That could lead to mass irregularity on one side of the system. Now that means there is a heavy mass which is existent on one side of the system, and that leads to when the lateral loads come, because the two sides would behave differently, one side with heavier mass and the other side with lighter mass, the amount of drift that would occur on one side would be much greater than that would occur on the heavier side. Now that would lead to torsion within the building structure or the system. So this is a torsional irregularity that could be induced under the lateral loading system. So what does this tell us? This tells us that our system should have mass distributed on that should be distributed evenly along the whole structural system. Another thing in the plan irregularities that are present in the structural systems. Now, when I am talking about structural systems, these are all types of structural systems. Either they are box type or frame plus shear wall. Now, that is there is a re-entrant corner. Now, if this re-entrant corner, which is present in the structural system, and they are not symmetrically placed, or they are placed such that the ratio of A by L is quite steep, or that would lead to the structural system behaving quite irregularly. For example, in the first case, A by L ratio is greater than 0.15 to 0.2, and in the second case it's also same, but it's T-shaped. The first one is L-shaped, and the third one is again A by L greater than 0.15 to 0.2. So these tell us that the value of A, lesser the value of A here, that would mean more regularity in the system and lesser re-entrant corners, and more reentrant corners would mean that the system behaves concavely to the mechanism of load transfer onto the now this will be explained a little more later on. uh, if for example our building has got is circular and the loads are coming from inside of the building towards the exterior of the building, the circular section may expand on one side, so it becomes a concave system. Now, if the system is convex originally, which is the case in the reentrant corners mostly, the uh, the reentrant corners, they behave such that there is a local torsion that's developing at the corners. Thereby, these corners tend to be exerted by torsional irregularities as well. The third one is the diaphragm discontinuity. Now, if the slab or the flooring is discontinuous, that could be on various accounts. It could be that there is a flexible diaphragm in the vertical components of the seismic resistant system on one end, and there is a rigid diaphragm on the other end. So there could be a mass resistance eccentricity between the two ends. Thereby, the two ends would be vertically discontinuous and irregular. Now, in the second case, there is an opening within the diaphragm, and this again leads to the corners and the edges of the slab section or the flooring being under concentrated stresses under the lateral loads. And in the third case, which is the diaphragm discontinuity with an opening not even at the center but at the end, so there is an eccentricity component also acting within the system. Now, the combination of all these three mechanisms could be much more dangerous and deadly for the structural system subjected to earthquakes. Fourth one is in the plan discontinuity is the outer plane offsets in the section. Now, these outer plane discontinuities are visible, for example, here in the building system, that there is a shear wall that is existent at the edge. Now, this shear wall is existent in along one direction of the system and not in the other direction of the system. The shear walls, if they were provided perpendicular to each other, would have been much more regular than when they are provided in single direction in the system. Now, then there is one more thing that's happening here, is that the shear walls are not present at every frame. Thereby, there is a discontinuity in the nature of behavior for every individual section of this structure. The worst case here for the plan discontinuity or the irregularity is the non-parallel systems of either the shear walls here, as is visible here, or it could be even in the frame system, but mostly it exists in the shear wall systems because they are longer. Thereby, for a building plan, if this type of non-parallel systems occur, then simply there will be more torsional forces generated in the system, and the plan irregularity would make it less earthquake resistant. This next type of irregularity, apart from the plan irregularity that's taken from IS 1893, is the stiffness irregularity. Here it could be seen that either, if you take the first picture, then there is a a greater height of the ground floor columns. In the second picture, the ground floor has got a lesser number of columns. In the third picture, there is a mid uh, story somewhere which is which has got greater height than other stories. Then in the fourth picture, what we observe is that there is a discontinuity between the first ground floor and the other floors. Thereby, there are certain things that what we mean is that the stiffness of certain floors is lesser. For example, in the first case, it's lesser in the ground floor, as compared, and in the second case, as compared to the other floors. So, this stiffness irregularity is quite dangerous for a structural system because it breaks the chain of the stiffness and degradation or decomposition along the joints or the nodes, whereby the moment redistribution tends to occur. So these with lesser stiffness, they tend to become soft stories, and these soft stories are then vulnerable to earthquake forces or to lateral loads, and they collapse much earlier due to the collapse mechanism which tends to build up within the structural system. Now, this collapse mechanism always starts with the least strong or the most stiff joint here, wherein the plastic hinge formations tend to develop in such column beams. So, stiffness irregularity is an important criteria which needs to be taken into account for earthquake resistant design. The second one in the vertical discontinuity is the mass irregularity, and what we see here in the first picture is that the heavier mass is located somewhere at the top story, and in the second picture the heavier mass is located in between stories somewhere. Now, this type of irregularity with mass being quite high in certain floors surely leads to the development of the vertical discontinuity of the behavior of the structure to the earthquake or the lateral loads. Now, with heavier mass, there would be more acceleration in those particular stories, and that would lead finally to the failure in such stories under earthquake loads. Another criteria adopted by IS 1893 is the vertical geometric irregularity. Now, here what we see is that it's given that L2 is greater than 1.5 times L1, where L2 is the lower story and L1 is the upper story length. Now, these lengths, if they are more in the ground stories than as compared to the upper stories, it becomes that there is a eccentric mass transfer towards one end of the building, and the building tends to rotate or undergo torsion under the lateral forces under such circumstances. This is same in the case with frame structures or with shear wall structures. Similar is the case when we are seeing that A by L ratio, if it's greater than 0.25 as in the first figure, with A by L greater than 0.15 in the second figure, and A by L greater than 0.1 in the third figure towards the top, the figures at the top, what we see is that if these are the ratios, then the system is moving towards vertical geometric irregularity as per code IS 1893. Next comes the in-plane discontinuity in vertical elements which are resisting the lateral forces. Now, when B is greater than A, for the lower story, B is the distance from the end to the, for example, a shear wall, and for the upper floor this is A. What we observe is that if B is greater than A, then the system is under vertical elements which are resisting the lateral force. These are the shear walls, both. They are discontinuous vertically. Next, what we observe is that for weak stories, when Fi is less than 0.8 times Fi plus 1, with Fi being the story strength, the lateral story strength, then we come to know that if the strength of a particular story is lesser as compared to stiffness being lesser, then this is a weak story. And if this happens, again there is a vertical irregularity in the structural. So what we know is that for a seismic structural configuration, we know for every structure the geometry, shape and size of the building matters. Next, the location and the size of the structural element, it also matters. And the third thing, the location and the size of the non-structural elements, they also matter. Now, geometry, best geometry that anybody could explain would be a rectangular cuboid one. The shape, everybody would say that the cuboid is the best shape. The size of the building, again depending upon the base area of the structure. Second, the location and the size of the structural elements. Now, ideally they would be symmetrical, and otherwise they would be such that we do not induce either stiffness, irregularity in plan or in vertical elevation, or we do not induce mass irregularity in plan or in vertical elevation. Now, knowing these, what we have to also know is that if there is a convex geometry of the structure, now this tends to behave much better than the concave geometry of the structural elements. Now, in a convex geometry, what is seen is that in the direction of the earthquake shaking, the structure tends to be pulled, while as in the concave geometry, the same structure tends to be tends to get constricted. So the convex geometry performs much better than in the concave geometry. Taking this into account, the shape of the structures can be explained further. Thereby, there are two configurations that a structure could have. One of this configuration is the simple configuration, wherein the structure would have a cuboid shape. So in such a shape, the behavior to the earthquake forces involves least amount of torsion developing within the structural system. In the complex configuration, which is shown here, the equilibrium forces, which is put in question mark here in both the shapes. One is a L shape and the other one is a circular shape with a cavity inside it. In both these shapes, the location of the equilibrium forces is difficult to be done, and moreover there is a complex formation of the structural forces in the system, and this complex formation of the structural forces involves shift in the eccentricity, the increase in the torsion. It also involves increase in the mass irregularities on one side of the structure. It also involves the increase in the stiffness irregularities during earthquakes on one side of the structural system. So, what type of design procedure should we follow to give in to us an overall structural design procedure for earthquake resistance? First is that we have to arrive at a simple overall geometry of the building that for a particular height of the building. Now, building should be well proportioned and it should be in keeping into view the tenets of acceptable upper limits of overall slenderness ratio as well as the plan aspect ratio. Now, both of these things are quite important. Slenderness ratio, it if we increase it beyond a particular limit, so there is a limit to the height of the building because there is a limit to the height of the columns or the shear walls or the masonry walls. Thereby, the building has to be well proportioned, keeping into view the slenderness ratio and its upper limit. We have to consider that we are always not making the columns and shear walls slender. Next is the plan aspect ratio. Now, this again has to be fixed such that the building configuration is much more symmetrical and the columns, they do not become such that if the aspect ratio is quite large, then the columns also have large aspect ratio. Thereby, the acceptable limit for the columns as per the ductility requirement, that also is crossed. So this that may induce another problem. Now, all these discussions that are available in earthquake resistant literature on acceptable seismic structural configurations, they also have to be taken into account. Now, in the second step of the design procedure, we had to adopt a structural system that will resist the vertical as well as lateral loads, offering direct load paths in both planned directions of the building. Now, this is understandable. It's preferable to use structural walls in RC building intended to resist strong earthquake shaking. Now, this is an add-on that we can, in an RC building with a structural system of low beams and columns, we can add structural walls as well, and these are the shear walls basically. They resist the strong earthquake shaking within the structural system. In the third step, what is determined is the preliminary sizing of the individual structural elements. So once we have decided the aspect ratio of the building, we have fixed the height of the individual floors and the overall height of the building, what we come to know is that then we have to now design each individual structural element. But first thing in designing these structural elements is that we need to place the columns first and then the beams. These are then based on acceptable slenderness ratios and cross-sectional aspect ratios, both that we have already discussed, and minimum reinforcement requirements. Now, the slenderness ratio of each particular column, for example, and then the cross-sectional aspect ratio of each column, for example, or of the beam for that matter, and then the minimum reinforcement requirement that would be utilized. Now, for example, here what we are discussing in this point is that if the spacing between the elements, for example the columns, is quite large, then the span is quite large, and if the span is quite large, then the beam dimensions tend to increase, the column dimensions also tend to increase. Then we have to take into account greater aspect ratios for beam and column, and then we have to again meet reinforcement requirements also increase. So and at the same time, if the spacing is quite less, then the space span is quite less, and accordingly, the sizes, the aspect ratios of beams and columns, they also reduce. But at the same time, what we are seeing that even the minimum reinforcement requirements, the reinforcement requirements are even less than the minimum reinforcement requirements. So we have to maintain a balance in sizing of the individual structural elements and deciding about their spacing. The fourth point is that we have to identify a desired collapse mechanism in which the building should deform in under the extreme conditions of collapse, if ever, when the earthquake shaking well exceeds the design earthquake shaking for the buildings for which the buildings are normally designed. Now, usually in the frame structure, now this is the collapse mechanism which we are talking about, plastic movement hinges are desired at the ends of the beam with good rotational ductility. Now, the hinge forms over a small length of a beam, often termed as plastic hinge length. This length depends on depth, span, and end connectivity of the member. Now, this is an important thing. Now, how do we expect the structure to fail under an earthquake? That's known as collapse mechanism. And we expect that the structure fails such that the beam ends fail, not the columns. Even if the things are failing at a particular time instant under an earthquake, it's the beam ends that fail first. And the plastic hinges are formed at the beam ends, not within the column, because the column is the overall vertical load supporting system of the structure. So the design has to be such that wherein the columns are much more stronger than the beams. In the fifth step, there is a basic structural analysis model of the building is prepared with the dimensions and the details obtained from the preliminary design strategies. We then impose a horizontal deformation on the building corresponding to permissible inter-storey drift at all stories and perform the elastic analysis of the building. We use concentrated loads at floor levels to push the building by the desired amounts. Now, this step is not usually adopted by common designers. Instead, they apply design lateral forces. First, they apply the design lateral forces, then perform the structural analysis, and then they design structural elements based on stress resultants obtained from structural analysis. In the sequence of the steps that are suggested in this procedure, the steps appear later as step 8, which will be shown in the next section. Now, what we come to know is that what we are doing actually is that we are, after making a basic structural analysis, we have now fixed the building dimension and its detailing from the preliminary design strategies, and then applied the loads, and then seen its analysis, under analysis, how it performs, what is its load taking capacity as compared to what is the demand of the earthquake. So this is somewhat like a capacity demand solution to the structural engineering problem under earthquake, wherein the capacity of the structure is tested to the particular load that's applied onto it. Next, what we do is that we perform seismic design. Now we have analyzed the structure. Now we have moved to the seismic design of all the structural elements of the building. For instance, in a moment resisting frame, we design the slabs of the building, then we design the beams, first for flexure, then for shear. Then we adopt the capacity design method for design of shear, which we have not studied as of yet, following the desired collapse mechanism identified. Third, we design all the columns, then the structural walls, and they have to be stronger than the connected beams, first for flexure, then for shear. Adopting again the capacity design method for design of shear and following the desired collapse mechanism which has been identified. Then we design the beam to column, beam to wall, and slab to wall, all these joints. Finally, we design the foundation of the building. We ensure that the soil underneath is capable of resisting the load from above under strong shaking, and that remains intact during the said shaking. Now this is not usually done by our structural designers, but this is an important point wherein the soil shaking also needs to be taken into account. The foundation shaking and the soil shaking has to be taken into account in unison for structural design or for earthquakes. Next, in step 7, we prepare the improved structural analysis model of the building with the dimensions, the details obtained from the design calculations which have been performed in the previous steps. We estimate the fundamental translational natural period of vibration T of the building, and we calculate the design base shear of the building. Now finally, after now knowing this, that we have the final drawings of the building from the improved structural analysis after the capacity demand analysis. In the 8th step, we apply the design seismic base shear VB on the structural analysis model. We finally check the adequacy of the design for all the structural elements, including beam, column, and beam wall joints. Now we have to verify if the desired mechanism is generated in the building through nonlinear quasi-static displacement pushover analysis of the building to begin with. Now what is this? This is a pushover mechanism that's applied onto the building, and now the system could be transferred. For example, the building could be incrementally loaded by pushes in the lateral direction, and the nonlinear analysis of the building done. We could also verify it from the nonlinear time history analysis of the building under different ground motions whose intensity spectrum are within the design shaking intensities and design spectrum respectively. Now this is just for verification purpose. We could adopt these two methods to the already static method of analysis that we adopt, which was much simpler. But for complex geometries, for structures which are much more important, structures which are quite large, heavy, and which involve a huge capital, structures which involve a large risk of life if they fail, then those structures need to be verified and checked by these analysis techniques as well. Now if the desired mechanism is not achieved, this is a no here. We make suitable change in the design. That's the choice of the structural system has to be changed, or the proportioning of the structural members. Now what is the proportion of the structural member, for example the column or of the beam? Now that needs to change to achieve what we want to achieve here in step number 9, and the proportioning of the structural members need to change. Now the above steps should be repeated for the new design if chosen, if all 1 to 9 has to be changed. If the desired mechanism is now achieved, then requisite ductile detailing may be performed and the drawings be prepared accordingly.